And so we'll go a little bit over, just some very basic theory. And then the main thing about IR is we'll just go through and look at examples of functional group absorptions. Okay? So the basic thing with IR is that, well, we know that delta E, right, equals H nu equals HC over lambda. The important thing is that that the energy of the light, or the frequency of the light, matches the same frequency by which bonds tend to vibrate or bend. And so when the frequency of the light matches that of a bond vibration, then light gets absorbed. Okay? And because different types of bonds are going to have different frequencies, they're going to absorb different frequencies of light. And so in a very simplistic view, in organic chemistry, when we talk about different kinds of bonds, we're talking about different functional groups, right? And so IR is essentially good at identifying different functional groups. Okay? We can kind of simulate simple vibrations by using this Hooke's law. And what that describes is just a single bond vibration where we have two atoms or two masses connected by a spring. Okay? The frequency of this vibration equals a constant times the square root of F, where F is the force constant of the bond, so essentially it has to do with bond strength, and mx and my are the masses of those two atoms. And so this whole part here is usually called the reduced mass. Right, so we multiply them together and divide it by the sum. So we can, look at some different examples here. So let's see. Yeah, the reduced mass. So basically what we see is that if F increases, what's going to happen to the frequency? It's going to increase, right? And if the masses increase, either one, it ends up that this denominator increases, and so the frequency in that case would decrease. All right. So here's just here's a summary of that. Here's a few examples. So if we go from a carbon-hydrogen stretch to carbon-deuterium, right, we increase the mass of the deuterium, right? And so then the frequency goes down. If we go to carbon-oxygen or carbon-chlorine, we're increasing masses, and so the frequencies continue to go down. Right, notice that these are in reciprocal centimeters, and this reciprocal centimeters equals 10 to the minus 4th over the wavelength in micrometers. It's proportional to the frequency. All right, other ones that we could look at here if we want to look at bond strength. So we're looking at that F term. If we go from a double bond to a triple bond, we see an increase in the frequency or increase in the wave numbers. Okay. Not all motions that we observe in the IR are just simple bond stretches, though. Are, so for example, CH2 groups can have all kinds of different motions. So if these two H's are stretching out in a symmetrical fashion, these are just called symmetrical stretches, but you're looking at this 3-bond motion, okay? Or one could be coming in while the other one would be going out. These are asymmetrical stretches. They can be coming together and scissoring, like bending like scissors. Or this one's called a rocking, where this one goes they're both going, together, back and forth. And these bottom two are bending out of the plane. So I think they're bending sideways or back and forth like this. And other examples are, say we have a benzene ring, the whole ring can flex and bend, and those types of motions can also be observed in the IR, though sometimes they're in a region where it's a little bit hard to actually, use them to characterize a molecule. Okay, one of the rules for IR is that to observe a stretch or a vibration, it must involve a change in the dipole. Okay? And the dipole depends upon a difference in, polarity and a distance. Okay? And so, for example, if we have carbon monoxide here, we have a polarity with a plus on the oxygen, minus on the carbon if we have this resonance form, and so we have this polarity, and as it stretches, the dipole is going to change because the distance between the plus and the minus are going to be changing. Okay? However, if we take carbon dioxide, and we have this symmetrical stretch where these are going to be both moving out at the same time and back in like this, then there's two dipoles, but they're opposite of one another, and so they would just cancel each other out. And so this would be what we call IR inactive. All right. Another example is that if we have... You do, but you can see it if it's not symmetrical, you can see like asymmetrical stretches and things like that.
Oh, so you're just showing that the symmetrical stretching of CO2 is...
Right. Yep.
Oh, the symmetrical.
The symmetrical one is IR inactive. Right, but you do see oftentimes carbon dioxide because... essentially what happens is you open up the sample chamber and you breathe in there, and it's different when you run your background versus when you run your sample, right? There's different amounts of CO2 by breathing into the sample chamber.
I try not to breathe too much.
Yeah, right.
Maybe on your bike.
Yeah, exactly. Another examples of those is if we have a terminal alkyne. This is usually IR active, but if we have a triple bond that's in the middle of some chain where it's much more symmetrical, then we don't observe the carbon triple bond stretch because it's not changing the dipole then. So this would be inactive. The position, like we talked about, are usually given in wave numbers, and this wave numbers is proportional to frequency. Okay, so the trends follow for what we talked about. Not only is the position important in the IR spectrum, but the intensity of the peak and the shape. All right, so the signal intensity usually increases when the bond is more polar. All right, so OHs, NHs, those are stronger absorptions than a carbon-hydrogen stretch. Though most organic molecules have lots of carbon-hydrogen bonds, so that ends up being quite a strong, peak, even though for an individual carbon-hydrogen stretch it might not be that strong. Carbonyl stretches, carbon-oxygen double bonds are very strong because this is a very polar bond. So when it stretches, it's easy to see. And then when we have hydrogen bonding, we get quite broad peaks. Because essentially when we have, say, an alcohol, and this is hydrogen bonding over like this, the strength of that, as the hydrogen bond strength increases, it's going to change the strength of the actual oxygen-hydrogen bonds. And so we end up with lots of different oxygen-hydrogen bond strengths, and so we see a whole bunch of overlapping peaks which make it very broad. Okay? All right, so here's just a table. This is out of our old organic chemistry text. I didn't trade it out. There's tables and everything in our textbook, and they goes into actually more details than probably what we're going to go through. But again, we can compare. We can look for those same trends that we just talked about. Some of the most important ones are the carbonyl stretches. OHs are easy to see, NHs. Some of these are very characteristic stretches, and they're easy to identify. And like I was saying, it's not only the position here, but it's whether it's strong or whether it's broad, or very broad, or
takes up the whole left side of the spectrum.
yeah, right. Or that it's weak to medium, so all of these things come to play. So I usually think of the spectrum of just some alkane as being kind of oftentimes the background, right? Because at least if our molecule has very much aliphatic portion, saturated portion, it's going to have these peaks, and then other functional groups are going to be added on top of this, right? So this is almost the spectrum with no functional groups, okay? And so the main things we see here is starting just below 300 reciprocal centimeters. This is a big carbon-hybridgen stretch, and this is where we see the stretch for the hydrogens that are attached to sp3 hybridized carbons. Okay? I guess I was going to go through some of this detail on the next one. The things here is that if we cut it about here, about 14 or 1500. This side over here is usually referred to as the functional group range, right? That's usually the part that's less busy and easier to identify peaks. This peak part from 14 or 1500 down to 600 is called the fingerprint region. It can be very complicated, and so they call it a fingerprint because, like our fingerprints, if you match a spectrum to another spectrum of a standard, then they should match, right? I guess the other things are just how the spectrum is shown. We have the wave numbers down here. On the y-axis is relative transmittance. And so either this is 1 or it might be 100% or in percent transmittance. And so when it's going along this one line or 100%, it means that all of the light is passing through the sample. So 100% transmitting through the sample. Huh?
Just no absorption of the light.
Right, there's no absorption if it's way up here at the top. And if we get to a peak and it goes down like this, it means if it gets all the way down here, very little light is passing through, so it's getting absorbed.
And you don't want it to hit 0, correct?
Well, if there's no bond that absorbs in that area, then it should be Oh, you mean at 0 all the way down to the
You
bottom?
don't want it to hit 0 because you're not sure if that actually completed its little peak or if it just
Yeah, I think,
concentrated.
yeah, if it's too concentrated, though you can run just neat samples in IR, but yeah, if there's 0 light coming through,
I guess we can mess it up using KBR pellets sometimes.
uh-huh,
With a little diamond tip one, you can run and not have to worry about concentration right on most of the time.
okay.
Never mind, sorry.
We'll see that more, I think, when we look at UV vis spectra too. If it's too concentrated, then it gives a problem.
Yep.
All right. So yeah, I guess you'd like to be able to see the tip of the peak. So we have, yeah. So this is the basic layout, and then if we just a couple of the peaks. So I already mentioned this one, carbon hydrogen stretches, but for sp3 hybridized carbons, down here these kind of peaks, I think they say are things like the this kind of scissoring motions and bending down here. So we have these kind of more complex motions that are down in the fingerprint region. Which mostly, well, sometimes they, if you read through the book in detail for alkanes, sometimes if you have, an isopropyl group or some special branching, they say there's peaks that you can identify, but I'm not going to go over that much detail. Yeah.
Can you explain why if there is a difference between KBR pellets and the diamond tip IRs?
I don't know what the diamond tip is.
Taylor, what's that word?
It's like the force knob, and you put sample on the top, and you just use force, and the diamond tip crushes it, and just, I'm not sure exactly what you call it.
Crushes a crystal or
It's a solid.
but it's not a KBR
Not
or
KBR pellet.
okay, so it's just if you have a solid sample.
Yeah, instead of mixing with KBR, you can just twist this.
Okay.
You set the pressure up with the instrument, it twists down, pushes the sample against the prism or the glass screen, and then it runs the light through that and samples it. So that way you never have to make a KBR pellet or do anything like that.
Okay, if you have solid samples. So what about it?
I didn't know if you had used both and knew the difference between both of them or why one was more beneficial than the other.
Well, I think it would just depend upon the nature of your sample. If you have a liquid sample, then you can just put a drop of that on a KBR on salt plates, right? The thing about using salt plates is you need to have a sample cell or sample holder that's invisible to the IR, right? So we use these inorganic salts and things like that don't absorb in the IR. There are solution cells. You can make up a solution and then, put it in as a solution. Or it sounds like this method is probably easier with solids than mixing up and grinding up the KBR and pressing those into the little windows and stuff. Yeah, so I think it just depends on the nature of your sample, probably the physical properties of your sample. All right, so this is just kind of the background. And as we add functional groups, we can see different peaks, okay, different absorptions. So this is 1-hexene. And the things that we can pick out that are different, right? Well, the things that are same, we still see this carbon-hydrogen stretch, right? Because there's lots of alkyl portion. But we see this signal on the higher frequency range, and so this is the stretch to the sp2 hybridized carbons, right? So as we increase the S character of the orbital, right, the bond becomes stronger, and so we're essentially changing that F, that force constant, right? And so it gets shifted to a higher frequency. Down in here, I think here and maybe here are carbon double bond stretches. And then you can just see this one is much more complicated down in the fingerprint region. You know, sometimes if I've seen seminars and stuff where people were, you know, where they were really interested in specific stretches, even carbon-hydrogen stretches, and so what they'd have to do is run one spectrum. They'd have to make another molecule that has a deuterium instead of a hydrogen at that position, and then look for changes in the spectrum. If we go to triple bond, okay, this top one is 1 octine. Right, so again, we see these same kind of things that we saw before, but way out here we see the carbon-hydrogen on the sp hybridized carbon, right? So again, that bond is strengthening, and so it's being observed at a higher frequency. For the terminal one here in the middle, this is kind of a unique range. We're seeing the carbon-carbon triple bond stretch. The bottom spectrum, I think, is just symmetrical, like this. Right? And so in this case, we can't even see the presence of the alkyne, right? There's nothing here. Of course, there's no hydrogen on the alkyne, so we can't see that. It's symmetrical, so it's IR inactive. So it basically looks just like an alkane.
What's the difference between the top and bottom spectrum? Sorry.
Well, they're two different molecules that I drew up there.
Thank you.
Yep. And the basic difference of the thing that we're looking at is one is terminal, so it has a hydrogen attached to the alkyne, and the molecule's unsymmetrical, so the stretch of the triple bond gives a change in dipole. So we see the carbon-carbon triple bond stretch, whereas when it's very symmetrical, right? So this is symmetrical. So the triple bond is IR inactive at that point. All right, we can also have alkenes in benzene rings. Right, so this is toluene. All right, and so we see a much more complicated carbon-hydrogen stretching region. Essentially, I always look right here at 3000, and the part below is for that methyl group, right? That's the sp3 hybridized portion, and above 3000, this is on the benzene ring. In here, we see the carbon-carbon double bond stretches. And we used to, when I learned IR, we spent a lot of time looking at these peaks right in here, which are called the overtones. And the patterns we used to look at a lot to discern different substitution patterns around the benzene ring. But I read some things more recently that said that that's not really that reliable. But if we see these overtones, I think we can at least say that it tells us that it's likely to be a benzene ring. And we used to look, and maybe there might be information like this in our text, down here, way down here, would tell us about substitution pattern as well. Okay, in the alcohols, this is one of the easiest ones to tell as well, as here's the OH stretch. Okay, and I was just before crossing this thing out, but I was just reading today. This is usually, so this is the hydrogen bonded OH, and this is kind of the free OH. And you can see this free OH usually if it has a very low concentration, or if you're in a nonpolar solvent, And so this down here would be the OH stretch if there is no hydrogen bonding. Okay? So then we see the CH, right? The bending. This is probably the carbon-oxygen stretch. Right? So we're just picking out the things that were on top of, well, this is one decanol, right? So we had the spectrum of decane before. We just added an OH.
So why the free OH have the higher big number than the hydrogen bonding OH?
Yeah, I think it's because when we just have the free OH, that's kind of like the pure oxygen-hydrogen stretch. But when we add hydrogen bonding to that, then it pulls the hydrogen towards the oxygen and weakens this bond, I think. So it's
We
at a
bond more at
right.
bond.
Exactly. And it's so broad because we have, hydrogen bonding is just not, every hydrogen bond is not the same, right? They're all in different strengths depending on how close they are and things like this, their angles and that kind of stuff.
I don't know if that's politically correct to say.
Huh?
I don't know if that's politically correct to say.
What?
All hydrogen bonds are equal.
Or they're not equal. We're not created equal. All right, so this is
Forgets about the fluorine hydrogen bond.
this is phenol here, right? So again, we see the OH hydrogen bonded, the free OH, right? We see the overtones, so we can identify that it's on a benzene ring, and probably this big, broad, strong one here is the carbon oxygen stretch, and in here is the carbon double bond stretches. And notice that, well, they're kind of overlapped a little bit, but these CHs are above 3,000, right? So these are the sp2 carbon hydrogen stretches.
Are we going to get into metal type inorganic complexes?
This is organic chemistry class. Who cares about that metal stuff?
I mean, it'll be pretty similar. I mean, and that's the.
If you want, at the end of the class, each of you are going to give a 10-minute presentation. So if you want to expand this into, some application, closer to what your research is or something like that, then that's great.
5 of us in here are inorganic.
I know. I know. Where are the organic chems? Where did they all go?
I'm alone.
Okay, down in that OH range, we can also see NHs. Okay, so here's butanamine. All right, and so one of the interesting things, I think, is that we usually see the same number of NH stretches as we have NH bonds. Right, so if we have this primary amine, we see at least these two peaks. It looks like there's some other peaks in that big thing, but we see the tips of two peaks. And I think it's probably from a symmetrical and an asymmetrical stretches. And then we have the CHs and a lot of the same things. We'd have to look this one up. It seems like that could be the carbon-nitrogen stretch, but I'd have to look that one up for sure. Down here is N-methylaniline. Right, and so there's only one NH, so notice that we see only one NH peak. We see both stretches for the methyl group. It's carbon-hydrogen stretches for the methyl group and for the benzene ring. And then we have the carbon-carbon double bond stretches, and then just a really complicated fingerprint region.
Complicated or it's goodness. So when we have something, we can.
Yeah, you can match it up if you had the. Okay, so one of the other really characteristic types of absorptions in IR are the carbonyl stretches. Okay, and so these are usually in the range of 1750 to 1600, and they're very strong. This spectrum is for cyclohexanone. All right, so I'm going to add in an extra slide here just to, I think that adds in an extra one. Trends in carbonyl stretches. Okay, so this cyclohexanone is kind of our standard or our beginning point. So this is at like 1750. Okay, so let's look at some general trends. So if we're looking at different carbonyl groups. Okay, we could have ketones or aldehydes, right? But if we put some other group attached, I'm just going to put a Y group over here. Could be for an amide or an ester or a carboxylic acid or something, or a carbon. If that Y group, if Y is more electronegative than carbon, then it's going to pull electron density away from the carbonyl carbon, and what happens is as we develop delta plus on this carbonyl carbon, the oxygen will tend to donate electrons down to that partial plus. All right, and when this happens, it actually strengthens the carbonyl bond. Right? So if it does that, is it going to shift to a higher frequency or lower?
Lower. It's going to require less energy.
Well, if it strengthens it, we're increasing the
Energy.
F value, exactly right. So this should be at a higher, yeah, or wave numbers or whatever. Okay, the other thing that can happen if this Y group, which if it's more electronegative, it's likely to also have non-bonding electrons on it. And so if those non-bonding electrons donate electron density to the carbonyl through resonance, we end up with a resonance structure that looks like this. And notice that in this new resonance structure, there's a single bond character to the carbonyl. Right? So this resonance here, if that's present very much, is going to weaken the carbonyl bond. And so this should cause it to go to a lower frequency. All right? So these two things can be taking place simultaneously, and they typically will be, right? It just depends on which one is more electronegative and which one is better at donating electrons, right? So which one of these two, things are taking place. All right, so let's look at some other trends here. So if we take a ketone and we add a double bond, or we add conjugation to it, all right, in general, this is going to allow this pi bond that's adjacent to the carbonyl to donate electrons, all right, to have resonance. And so should the new absorption, should it be at lower wave numbers or higher?
Lower.
Lower, right? So this comes out at about 1674 reciprocal centimeters. Okay. If we have an ester, right, we have a more electronegative atom, but there are non-bonding electrons on that atom as well, right? So these two, factors are kind of opposing one another. For esters, the electron withdrawing is stronger than the electron donating. So this is going to strengthen, right? So this goes up to 1750 to 1735. Right? Of course, if you added conjugation, it would go back down, right? And if we compare that to amides, right? The nitrogen is less electronegative than oxygen, and it's also a better electron donor through resonance, right? So now the electron donation becomes more important. So why is nitrogen better at donating electrons for this kind of resonance?
It's more happy with a positive charge.
Yeah, it's less it's more electropositive than oxygen, right? So it can better hold a plus charge. All right, and so amides are usually more at about 1695 to 1650. All right, so notice that the ketone is kind of in the middle. The esters are on a higher frequency. The amides are on a lower frequency. And then I think aldehydes are pretty close to where ketones are. All right, so let's look at some examples. All right, so here was just cyclohexanone. We already looked at this one. Right, so here's the carbonyl stretch, 1715. Here we got the the CH stretches, right? SP3 hybridized. This kind of thing down here, I think, is what they call the, what is it? It's an overtone as well. And so I think 1750, I think if it's just about double what the carbonyl stretch is. And so it's just twice the value, and that we see a little kind of more like an artifact peak out there. Okay, the next one is cyclohexenone. All right, and so we see the sp2 carbon hydrogen, oops, that's a 2 stretch. I think they look almost the same here, but I think this is supposed to be at just about like 1720. Which it should go actually the other way, shouldn't it? It should go lower, it seems like.
Lower with number.
Yeah. I don't know. It looks, I'll put a question mark by that. Right, it should go to lower. Should go lower. It's pretty hard to tell. All right. Aldehyde. Okay, we have the carbonyl stretch. But the thing that's easier, together with the carbonyl stretch that we can pick out for aldehydes is this pair of peaks right here. These are the carbon hydrogen stretch for the aldehyde peak. Right? And there's always two of them, and they're usually at about 28, 30, and 2695. So this combination of carbonyl and this pair of peaks, which are kind of just on the low frequency range of where we usually see the carbon hydrogen stretches for sp3 hybridized carbons. then those peaks are characteristic of an aldehyde. So this is benzaldehyde. Right, so we have in this one, very small carbon-hydrogen stretches for the sp2 hybridized carbons. Okay, the next one is ethyl benzoate. So it's an ester. Right, so we see both sp2 and sp3 bonded hydrogens. We have the ester carbonyl, and so for esters, there's 2 carbon-oxygen stretches. Okay, and even though the fingerprint is super complicated, I would look in here and I might pick out this peak and this one, here, here, and here as being strong and slightly more broad than the other peaks in there. So I would guess that these are likely carbon-oxygen stretches. So I don't think it's not 100% assignment, but if you see stronger, broader peaks down in there, I think it does suggest carbon-oxygen stretches. And then we can see some peaks in here for the overtones as well, which fits for having a benzene ring. All right. Carboxylic acids have super broad OH stretches. Okay, so the OH kind of stretches all the way over this whole region. So this is benzoic acid. Has the carbonyl stretch, probably the carbon-carbon double bond stretches, and I guess these show partly very strong, I don't know why they're so broad, really, but what they talk about is that they tend to form dimers. Like this. Between the 2 carbonyls, right? They dimerize, and so they form some very strong hydrogen bonds. Yeah. All right, and the last one that I have here is an amide. So we see the carbonyl stretch. We see 2 peaks because it's a primary amide. There's 2 NHs. Right? We see the carbon-hydrogen stretches. They're all below 3,000, so we know there's no benzene ring. All right. Yeah.
So why we can't see the free OH in the benzoic acid right now?
Why can't we? Because I don't know if you do very much for the carboxylic acids. I think that they form these dimers very readily. And so there isn't very much free OH in for the carboxylic.
It's too small in the sample, right?
Yeah. All of the examples I have. So I think, if we can just kind of point out some general ranges, most times that's all you really need to know, right? So if we start at the left down here, we have these broad OHs and NHs, right? Somewhere in here we saw the sp hybridized carbon-hydrogen stretches. And then in here, the sp2 carbon-hydrogen stretches. These are the carbon sp3 stretches. In here, we saw the aldehyde carbon hydrogen, right? The 2 peaks down in here. In this middle range, the main things in here is we see triple bonds. So carbon-carbon triple bonds, or I didn't show you an example, but nitriles show up very strongly in here. Right? And then in the, let's see, this is 19, 18, 17. In here, we see the carbonyl stretches. And then down at like 1,000 to 1,200 in here, we can see the carbon-oxygen stretches. All right, and if we know these, you know, we can get by with most of what we need to do. Right, but there's much better tables and stuff in the book, in the text and stuff too. All right, this will be our whole one day of IR. All right, so I just have a couple of simple examples here. Nothing's even complicated. I think it could be.
So that'll narrow it down pretty good.
And here, C8. Right, which ones can we rule out?
A and C.
A and C.
Yeah, A and C we can rule out.
Pretty high, so.
Yeah, and then between B and D, it's all a matter of whether this is really a carbon-oxygen stretch or not. Right? So I would say, I think it was B. All right, what about this one? Yeah, it's not A, right?
Get rid of D.
Get rid of D.
And also get rid of C. Double bond.
There's no double bond, right? So B, right?
Setting a trend.
Well, that's pretty easy. Oh, it's always B. All right, so that's all the IR slides I've got. If we want, we could go work a couple more problems on that website,
Sure.
just for fun.
I was gonna ask, next week, there's supposedly gonna be the exam?
Yeah,
for-
that's the exam.
Oh.